For our second section here, Module 12.2, continue on with our topic of deflection of beams from Chapter 9, but now looking at superposition, theorems, and applications. So objectives within Module 12.2, the method of superposition, we're going to look at the statically determinate beams and statically indeterminate beams. Then we'll move on to our moment area theorems, looking at general principles, cantilever beams and beams with symmetric loadings, and then look at our beam bending moment diagrams by parts. From there, we'll then move on to our moment area theorem applied to beams with unsymmetric loadings. We'll look at our general principles, go over the maximum deflection, and take a look at the statically indeterminate beams. So again, within this module here, go over the theory related to these topics above here, talk about our governing equations, go through some practical applications, and then do some problem solving together. So let's take a look at the topic of the method of superposition. So when a beam is subjected to several concentrated or distributed loads, oftentimes it's going to be convenient for us to compute the slope and deflection caused by each individual load. Now the slope and deflection due to the combined loads are then obtained by applying the principle of superposition and adding these individual values of the slope or deflection corresponding to various loads. So now let's take a look at the visual representation of our method of superpositions in this diagram on the top of our slide. So we can see on the left in B, we have a combined load here of a concentrated load of 150 kilonewtons and a distributed load of 200 kilonewtons per meter. We can see that it has a support here at A and at B, and that our concentrated load of 150 kilonewtons is located here at this point D. So we can say that the beam's loading can be obtained by superimposing deflections due to that concentrated load and the distributed load. So there's our concentrated load and distributed load. Looking at these individually, our concentrated load is this 150 kilonewtons located 2 meters from our support at A at this point D. We see the whole beam has a length of 8 meters, and this is going to now be plus, we separate out over here, we can take a look at a distributed load of 20 kilonewtons per meter. And again, we can still see our distances right there to point D and the total length of our beam. So what does our principle of superposition say? Well, it says that deformations of beams subjected to combinations of loadings may be obtained as the linear combinations of the deformations from the individual loadings. So we can then take a look at, like we saw up here, the individual loadings and look at those deformations from each of those. So this procedure is facilitated by tables of solutions for common types of loadings and supports. So we need to double check those tables, make sure we're using them for the right application for our specific problem. So now let's take a look at an example problem for this method of superposition. So we'll take a look at sample problem 9.7. So you can see in this problem here, we have this diagram where we have a distributed load from C to B. Now we can see the distance of the whole beam is L, and our distance from C to B is L over 2. So half of the beam is going to be that distributed load W. Now, what they ask us and tell us in the problem statement here is that for the beam and loading shown, they want us to determine the slope and deflection at point B, which is our endpoint over here. So for our solution, what we're going to do is superimpose the deformations due to loading 1 and loading 2 as shown. So again, we're going to separate this out. So what we can say is this final loading that we're interested in here with our distributed load from C to B, this is going to be equal to loading the entire beam, a distributed load across the entire beam from A to B, plus a distributed load on the bottom going the opposite direction from A to C. So basically what it's saying is this load, essentially minus this load, because it's going to have an opposite sign convention right there, is going to be equal to this distributed load here. So likewise, if we're looking for our slope and our deflection right here, we can see, okay, well, what we're looking for, this y sub b, this deflection and this angle theta sub b is going to be equal to our y sub b1, theta sub b1 plus y sub b2, theta sub b2. We can see this is going to be bending this down with this whole distributed load here, whereas if we have this little partial load right here from A to C, this is going to be bending it up there. So we're going to add this deflection and this deflection to get our y sub b total, and we're going to add this angle here, theta b1, plus our theta b2 to get our theta b that we're looking for this slope and deflection at point B. So what we want to do with this problem is go back to our governing equations we saw at the beginning of the chapter in order to calculate our theta sub b and our y sub b. So again, our theta sub b is our angle here and our y sub b is our deflection there. So we can go back to our general governing equations and we plug in for those. We'll end up with, we look at this for just our loading 1. So recall our loading 1 is we had our distributed load from A to B, and this is the load W. So what this ends up being for this cantilever beam here with a length L is we have that theta sub B1 is equal to a negative W, which is our distributed load, times that length L cubed all over 6 EI. And for our deflection at B, our y sub B right here, our y sub B1 is equal to negative W, that distributed load, times our L to the fourth all over 8EI. So now for our loading 2, we come down here for our loading 2, and we see that our theta sub C2, so this right here, this angle here, this is going to be equal to our W, there's our distributed load W right there, times our L cubed all over 48EI. And our Y sub C, which is at this point here, our Y sub C2, this is equal to our WL to the fourth, our distributed load times our length to the fourth, all over 128 EI. Now, if we're looking at the second half of that from C to B for our loading 2, the beam segment CB, the bending moment is 0, you only have the load at the beginning from A to C, and the elastic curve is the straight line. So from that point there, we can say that our theta sub B is equal to our theta sub C for this part loading 2. So this right here is going to be equal to our theta B as well. So that angle isn't going to change, again, because this is going to be a straight line going from B to C, so it's going to be that same angle. And we can say that our Y sub B2 out here, now we can see, well, it's going to be this Y sub C2 down here, which we have this value for, so that's our Y sub C2 right there, plus this distance over here, going from that point there up to our end here. So that's going to be Y sub B2 is going to be a combination of this Y sub C2 and this distance here. And this distance here is given to us by our WL cubed over 48 EI times L over 2. So we add those together to get that total deflection at the end there, our Y sub B2, and this is equal to 7 times our distributed load W times L to the fourth all over 384 EI. So now with that information we've obtained from those relationships, we can now use our method of superposition. So the actual loading is equivalent to the superposition of the two distributed loads. So this is what we're looking for in the end here is our Y sub B and our theta sub B. This is the same as adding together this Y sub B1 with our Y sub B2 and our theta sub B1 with our theta sub B2 here, which we now have relationships for that we use from the general governor equations from the previous section of this module. And we came up with the relationships over here. So now we can say that our theta sub B is equal to our theta B1 plus theta B2, which again, these are the ones we just obtained. Our theta sub B1 is at negative W, our distributed load, times L cubed all over 6 EI plus our W times L cubed over 48 EI. We add those together, and our theta sub B is now this negative 7 omega L cubed over 48 EI. And our Y sub B is Y sub B1 plus Y sub B2. So there's our Y sub B1 plus our Y sub B2 there. So this is equal to a negative W times our L to the fourth all over 8 EI plus now we have 7 omega, or W, sorry, L to the fourth all over 384 EI there. We can add those together and we find that deflection, our Y sub B that we're looking for here is going to be negative 41 WL to the fourth, where W is that distributed load, all over 48 EI. Now what we want to do is we want to double check our sign convention with all this along the way. So if we were using a standard coordinate system where we had our X positive to the right and our Y positive going up, then it makes sense here that our Y sub B is going to be a positive number, and our Y sub B, sorry, Y sub B is going to be a negative number because it's going down here. Our Y sub B is going to be a positive number for Y sub B2, so our Y sub B at the end is going to be negative. So we want our total Y sub B at the end to be negative, which it is. And we said for our loading 1, we want our Y sub B here to be negative as well. Yep, that's negative right there. That's a double check. And our loading 2, our Y sub B2, this is going to be positive, which it is. So that's a good double check. Same with our theta sub B. So our theta sub B in the end should be negative, which it is. So that's good. Our theta sub B1 for our loading 1 is negative. Check. And our theta sub B2 should be positive, and this is a positive check. So sign convention is going to help us, and always good to reference back to your chosen coordinate system to make sure that everything is correct, especially with the superposition in a case like this where we'd have some going in our positive y direction and some going in our negative y direction. Now we can also use the method of superposition for statically indeterminate beams as well. So that's what we're going to take a look at in this diagram we see below. So within this, we're going to analyze the indeterminate beam by superimposing two determinate cantilever beams subjected to, as we see in part C here, a uniformly distributed load, our W here, and in part D right here, there's our redundant reaction, which is making this being an indeterminate beam. So because we have this support at the end, this reaction at the end here, this is what makes it the indeterminate beam. So this is where our method of superposition comes into play here, and this may be applied to determine the reactions at the supports of this statically indeterminate beam. So if we designate one of the reaction as a redundant and eliminate or modify the support. So that's what we've done here by looking at this as two separate loads here. We got our distributed load and we have a redundant load over there. So we designated one of these as a redundant. So there's a redundant load right there, and we've eliminated it from this part right here where we just have our distributed load. So then we can determine the beam deformation without that redundant support and treat the redundant reaction as an unknown load, which together with the other loads must produce deformations compatible with the original supports. So if we go back up to our diagram in part B up here, and we can see that redundant support there, reaction at B, what this tells us is if that wasn't there, this would deform and we'd have a deflection at point B, but because we have the support there, our y sub B is going to be 0 because it can't deform, it can't move at that point B. So next, let's take a look at our moment area theorems. So within this, the geometric properties of the elastic curve, which we've discussed before, this can be used to determine our deflection and our slope. So recall our deflection is typically a y, and our slope we're looking at here is our theta term. So if we consider a beam subjected to arbitrary loading, we can take a look now at our equation 9.15 in our textbook, where we have our d theta dx, our change in our theta with respect to x, is equal to our d squared y, our second derivative of y with respect to x, d squared y dx squared, which we know is our m over EI. So we can say that our d theta dx is equal to m over EI. We can rearrange this slightly and move the dx over to the other side, multiply it over here. So we have d theta is equal to m over EI dx. And then what we can do is we can take the integral of both sides of that equation. So we'll take the integral of our d theta from our theta sub c to our theta sub d. And this is equal to, when we take the integral of our right-hand side of the equation, the integral from x sub c to x sub d. So this is the area of interest that we're looking at here for our example problem on the left. This is of our m over EI dx. So now we do out those integrals, and the integral of d theta with those limits of integration becomes theta sub d minus theta sub c. And this is equal to that integral of the right-hand side over there from xc to xd of our m over EI dx. And this relates back to our equation 9.16 in our textbook. So now let's go back over and take a look at this diagram and our figure on our left side. So we'll look at part A first. In part A, we have this sample loaded beam. So we can see we have distributed and concentrated loads going from A to B across this beam. Now in part B, what we have here, this is a plot of our m over EI. So our m over EI right here from our equation 9.15 in our textbook as our y-axis going across, and we have our x going across our x-axis here. So this right here shows the plot of our m over EI curve. So now in part C, what we have down here, we can see is the elastic curve showing the slope of C and D. So that's our theta C and our theta D right there. And last down here in part D, what we have is the elastic curve showing the slope at D with respect to C. And this is going to become important here because that's how we're going to solve for this with D with respect to C, is by solving for our theta D and our theta C first, and then using that relationship to get this theta D over C. So this brings us to our first moment area theorem, where this theta D over C that we see in this diagram here, this is the area under our M over EI diagram. So this area right here between our points C and our D. So now let's take a look at the second moment area theorem. So if we consider 2 points on this curve up here, our P and our P prime on this curve from A to B, and that the fact that these 2 points P and P prime lie between our point C and our point D on this curve, then what we can notice here is there's a distance between P and P prime of this dx. So that's the distance between our points P and P prime that fall on this curve in between points C and D. Now, if we were to come in and take a tangent line at P and P prime, we can see we have this straight line here that goes across as our tangent line to P that comes down here, and we can see that this intersects through the vertical line at point C right there. And we do the same thing at P prime. Here's our tangent line right here. It comes down, and now this intersects down here for the vertical line going down through at point C. So the distance between those two lines we can see over here now is our dt. So again, these are the lines that are tangent at P and at P prime there, and the distance between these two, if we're looking at our vertical axis, is this dt. Now, since the slope theta at P and the angle d theta formed by the tangents of P and P prime are both going to be small quantities, then our d sub t over here is going to be assumed to be equal to the arc of the circle of our radius x1. So now let's take a look at our diagram on the bottom left here. So with this diagram here, we can say that our expression x1 times our m over ei times dx, this is going to be the first moment of the shaded area with respect to c. So we can see there's our m over ei on our y-axis, there's our x1 dx, and there's our shaded area. So again, the expression here is going to be that first moment of the shaded area with respect to c. So now let's take a look at our second moment area theorem that we have illustrated here in our diagram on the top right. So we can see there's our m over ei curve right there. There's going from c to d. So we can state that according to this theorem, our tangential deviation t c slash d, which is c with respect to d, this is going to be equal to the first moment with respect to the vertical axis through c right there, of the area under this curve from C to D. So that's this shaded area right here. So as we saw earlier, the tangents to the elastic curve at P and P prime, so there's our P and P prime from that elastic curve we saw earlier, are going to intersect a segment of length dt on the vertical through C. So there is dt on the vertical through C. So from that, we now have this relationship expressed in our equation 9.18 in our textbook, that dt is going to be equal to our x1 d theta. So there's our x1 and our d theta right there. This is equal to, when we plug in now, x1 times m over ei dx. So that's a relationship relating back to our equation 9.18 in our textbook. So now we also have an expression in equation 9.19 for our tangential deviation of c with respect to d. So for our tangential deviation of c with respect to d, this is our t of c slash d, which we can see down here in this diagram that we saw before. And this is equal to the integral from xc to xd of this expression from our equation 9.18, which is our x1 times m over ei dx. Now from our second moment area theorem, the tangential deviation of c with respect to d, this value down here, is equal to the first moment with respect to a vertical axis through c. So we can see there's our vertical axis going right through c of the area under this m over ei diagram between c and d. So that's that shaded area right there. So now let's take a look at cantilever beams and beams with symmetric loadings. So let's take a look first at our cantilever beams. Now in cantilever beams, the tangent to the elastic curve at the fixed end, A, is known and can be used as a reference tangent. So here's our fixed end at A. So for this cantilever beam situation, we can select the tangent at A as the reference. So there's our reference tangent right there. So with our theta equal to 0, this line comes straight out like we see here. Now our theta at D is going to be equal to our theta of D relative to A. So we can see that right here. Here's our theta sub D, our angle at this point D. Now D could be any arbitrary point in the beam, so this will be the slope at the beam at any point D. And again, it's defined by this theta sub D is equal to D over A. And this can be obtained using the first moment area theorem. Now, on the other hand, if we're looking for our deflection, our y sub d, the deflection yd of point D, which again is any arbitrary point going along this beam right here, is going to be equal to the tangential deviation, our TDA. This is going to be measured from the horizontal reference tangent at A and can be obtained using the second moment area theorem. So we can see there's our y sub d is equal to this TDA right there, and that's that distance there at some point D. Now let's take a look at the situation for a simply supported beam. So we can see this in our diagram here, where we have it supported here simply at A and at B, and we can see our symmetric loading of our P's right there. So in a simply supported beam AB with a symmetric load, what we can tell here is that at the tangent at center C right here, this must be horizontal. This is by reason of symmetry and can be used as a reference tangent. So we can come up here, this is that horizontal reference right here at that point C in the center. Now, since our theta sub C is equal to 0 right here at our horizontal, then the slope at B is going to be our theta sub B. So there's our slope at B right there, our theta sub B, and this is going to be our theta of B relative to C. And this can be obtained by using the moment area theorem. So we have this relationship here. We have the simply supported symmetric loaded beam. Select the tangent at C as the reference. So there's our tangent at C as the reference. This says that theta sub C is equal to 0. So therefore our theta at B is going to be equal to theta of B relative to C. Now we can also see here that our YB, our max, is equal to the tangential deviation, or our T of B relative to C. And this can be obtained with our second moment area theorem. So we can see this tangential deviation, or TB relative to C, over here in our diagram right there. We can see that's from our reference tangent up to our point B right there. Now, if we did want to find our Y sub D right there, which is the deflection at D, what we know is that the slope at any other point D, so some arbitrary point D right here, of the beam is found in a similar way. So this deflection, our Y sub D, is given by the difference between our T sub DC and our T sub BC. So now I want to go ahead and take a look at our bending moment diagram by parts. So the determination of the change of slope and the tangential deviation is simplified if the effect of each load is evaluated independently. So we'll break this into individual sections and evaluate these on their own. So we can construct a separate diagram, moment over EI diagram, for each of the loads. So what we see with this is that the change of the slope, our theta of D relative to C, is obtained by adding the areas under these individual diagrams. And our tangential deviation, our TDC, is obtained by adding the first moments of the areas with respect to the vertical axes through D. And how we define this is that the bending moment diagrams plotted from these individual loads is said to be drawn by parts. So we can come over here on the left-hand side to our diagram. We can take a look at our simple shapes. These are the areas and centroids of common shapes. So we have a rectangle. So we can see with our rectangle, we have our basic dimensions. We have our width B, our height H, and our distance to our centroid here at the center C. They give us a definition for our area of BH, and our C right here is our B over 2. So it relates it back to those dimensions there. We do the same thing for a triangle. So again, we have our width B, our height H, our distance C here. Now our C is equal to our B over 3, where our height is B times H over 2. Then we have a parabolic shape here, where again we go through and we can take and relate all of these for our C's back to our widths here. Same thing for a cubic and for general as well. So for all of these, we can reference back this diagram for these shapes in order to evaluate these each individually. So now let's look at the situation if we're dealing with beams with unsymmetric loading. So we can see this in our diagram on the top left, where we have an unsymmetrically loaded beam. You can see here it's simply supported at A and B. We have a concentrated load at P, and we have a distributed load over here of W. So in part B of this diagram, we can see that the application of the moment area method to find the slope. So there's our reference tangent right here coming off of A. There's our T of B relative to A, and there's this angle theta sub A. So we can define the reference tangent at support A and evaluate our theta A by determining the tangential deviation at B. There's our tangential B with respect to A. So that gives us this equation right here where our theta A is equal to that tangential deviation at B with respect to A divided by L with a negative sign in front of it. Now the slope at other points are found with respect to the reference tangent, so our theta sub D at some other point along here is equal to our theta A plus our theta D relative to A. So the deflection at D is going to be found from the tangential deviation at D. So we come over to our diagram here and we see the deflection at this point D here, and similar triangles are used to determine our Y sub D. So we have this relationship that our EF over X, so we come back over here, this is our EF right there, there's point F, there's point E, divided by our X, there's our X value right there, is equal to HB, so there's our HB right there, over L. So that is our similar triangles right there. So we can rearrange this and we can say now that our EF is equal to X over L, so our X over our L right there, times, there's our tangential deviation right there. So from this, what we can say is that our Y sub D is equal to our ED minus EF, which is equal to that tangent right there of D relative to A with respect to A, minus X over L times our tangential deviation of B relative to A. So determining this maximum deflection, we can take a look at our diagram shown here. So in part A, if we want to determine the maximum deflection using our moment area method, part A, we have the maximum deflection occurring at this point K right here, where we can see at K right here, we have our theta sub K is going to be equal to 0, which is where now this theta of K relative to A, this angle right here, is going to be equal to our negative theta A right here. So now if we move on to our diagram in part B, we can see that our point K right here, this is located where the maximum deflection is equal to the first moment of the shaded area. So there's our shaded area from A to K with respect to A. So we can see on this here that our area is equal to that theta of K relative to A right here, which is equal to our negative theta A. So continuing on with our discussion of maximum deflection. Our maximum deflection occurs at that point K where the tangent is horizontal, as we saw in that previous figure. So with this, we say our theta sub A is equal to this value here of negative T of B relative to A all over that length L. And our theta sub K is equal to 0 at that point because it's tangent at the horizontal, so that's equal to 0. And this is equal to our theta A plus our theta of K relative to A. So we can rearrange this expression here. And what we can say now is that our theta of K relative to A is equal to our negative theta A. We also know that our point K may be determined by measuring the area under that M over EI diagram, and this is going to be equal to that same negative theta A. And we also know that we can obtain our Y max by computing the first moment with respect to the vertical axis through A of the area between A and K. So next we want to take a look at the use of the moment area theorems to determine reactions in aesthetically indeterminate beams. So we can see in our diagram here, we have a statically indeterminate beam with a uniformly distributed load. So here's our W, our uniformly distributed load, but it's statically indeterminate because we have this extra reaction right here for the support at B. So that makes it statically indeterminate. So with this here, what we can do is we come down to our diagram for B, C, and D, and we can see in B what we're doing is we want to analyze the indeterminate beam by superimposing two determinate simply supported beams subjected to, as we see in part C here, a uniformly distributed load, so there's our W right there, and in part D, our redundant reaction. So we can break this apart and solve it this way, and that's how we can utilize this moment area theorem to determine these reactions in the statically indeterminate beam by breaking it down into those two different parts like we see here. So looking at the details of how we do this to determine the reactions for the statically indeterminate beams, what we can see here is the reactions at the supports of the statically indeterminate beams are found by designating a redundant constraint and treating it as an unknown load, which satisfies the displacement compatibility requirement. So then we can use this M over EI diagram, drawn it in parts. The resulting tangential deviations are superimposed and related by the compatibility requirement. Now with the reactions determined, the slope and deflection are found from the moment area method.